Our next and last section, this was 3 point something. It will be about affine subspaces of Rn. Now, the idea, well, as I said, to reach the strongest optimization theorems, we will need separation theorems. Why is that? This widely used picture in economic theory, well, this is the budget set. You have indifference curves. Well, suppose utility is increasing in this direction. Well, then the utility of an agent whose utility is, well, the utility of an agent whose utility is represented via these indifference curves, subject to the budget constraint, well, if you take this, well, that's not a maximum because this is a higher indifference curve and it has points within the budget set and so on, where you have this tangential point. But I have chosen the preferences which lead to these indifference curves to be convex. What does that mean? Better than or equivalent set, that's convex. The constraint set, that's convex. Then you have some line in R2 which separates this convex set from this convex set. And that separating line that actually contains the maximizer of some standard but famous problem. So we need, well, a line is a separating object in R2. In R3, if you have a line that does not separate the space into two. What does separate R3 into two? It's a plane. Or if you go back to the one-dimensional case, what separates a line? It's a point. So here, this is a one-dimensional object. A point is a zero-dimensional object. We'll see what that means. We will formalize that. That's the separating. Here, R2 is two-dimensional. Line is one-dimensional. That separates. R3 is three-dimensional. Plane is two-dimensional. That separates R3 into two half spaces. So, well, then we expect in Rn that there should be some n-1 dimensional counterpart of a point, line, plane in R1, R2, R3, which separates the space into two. But for that, we first need to generalize points, lines, planes, and their counterparts in higher dimensions. Because in R3 we have points, we have lines, we have planes, and we have R3 itself. Okay? So in R2, let us take a line. well, we have gone through this exercise, is the set of points on this line a straight line, something quote unquote linear? Do they form a subspace of R2? No. Well, there is no zero vector on here. In fact, if you add 2 points on here, they will not lie on the line again. They will lie elsewhere. So it's not closed. Addition, usual addition of vectors, is not a binary operation on this line. But every line has something which is parallel to it and passes through the origin. Will the set of all points on this line, will they form a real vector space under the usual scalar multiplication and addition? They will. For a point, is this point a real vector space? Well, if you take it as the point 0, it is, otherwise it's not. Okay? But this line can be written as this line shifted by some member. This point can be written as this zero-dimensional real vector space, this subspace of R2, plus some fixed number. Well, the same in R3, if you have a plane not containing the origin, that will not be a subspace, but one which is parallel to that and contains the origin, that will be a subspace. So you can take that subspace and shift that so that, since they're parallel, they will coincide. If you just find the right, if you add to 0 something on the plane which does not contain the origin, well then the plane passing through the origin, that will be translated to the other. So, well, we'll use this observation in defining an affine subspace, but let me first remind you of the following definition and proposition. Let V plus dot be a real vector space and W, a non-empty subset of V, we say that W is a subspace of V if W, now under the restriction, is a real vector space itself. But this means I'm using the same symbols for this, but this means plus should be binary operation on W. That is, if I take 2 points, x, y, in W, x plus y should be there. This also should be a scalar multiplication for W. That is, if I take any real number r and any x in W, Rx should be in W. Now we will actually take everything we know about subspaces in Rn at least, as given to us from linear algebra, but let me remind you of the following. Be a real vector space and W in V. Now, W is a subspace of V if and only if. Here, the non-emptiness, we need that, but that's given in here. For all xy in W, x plus y is in W, and for all r in R, and for all x in W, Rx is in W. Will these conditions, these two conditions, imply, for example, that the zero vector is in W? Now, W is non-empty. Let me take any x in W. What do I know from these two? If I take R as -1, -1x, that will be in W. But -1x, that will be the negative, the additive inverse of x, minus x, that will be in W. X plus minus x, that will be 0, that will be in W, and so on. So this is just a quick reminder what we'll be using. Now we can start with the definition of an affine subspace. Let M be in Rn. We say that M is an affine subspace of Rn if it's the shifted form of some subspace W. That is, if M is equal to some singleton set M in Rn plus W for some M in Rn and some subspace W of Rn. If this is the zero vector in R3, this will be just a point M, a single point. If this is a line passing through the origin in R3, this will just be a line which need not pass through the origin. If this is a two-dimensional subspace, that is a plane passing through the origin, containing the origin, this will just be some plane in R3. Well, if this is the entire R3, then this will be the entire R3 as well. Okay. Now, firstly, the first proposition, let M be an affine subspace of Rn with M equal to singleton M plus W for some M in Rn and some subspace W of Rn. Now, well, here this says for some M in Rn, but will it be in cap M? this singleton M? Well, always, because this is a subspace and it contains 0, M plus 0, M, that will be in here. M, that will be in M, and now here, this is the definition, but it would be nice to be able to express this W in terms of cap M itself. And in fact, it turns out that W is equal to just M minus M. This is not the set difference. This is just the algebraic. That is, this is equal to the set of all x minus y's such that x, y both belong to M. Now, well, for the sake of completeness, let's write this as well. As 0 is in W, the 0 vector in our N, M is equal to M plus 0, and this belongs to M plus W, but that's M. Now, this seems to be a bit more intricate. Well, here we have a set equality, so we'll first show that W is a subset of M minus M, and then that M minus M is a subset of W. To do that, assume that X is in W. So the question is, can I write X as the difference of two members in cap M? But members in cap M, they will be of the form M plus something from here. What are natural candidates for 2 points in here, say W1 and W2, such that W1 minus W2 is equal to X? M plus X, that will be in here. X is in W. What else do I need? M plus 2X. But 2X, that will be in W, since W is a subspace. Now, 2X is in W, since W is a subspace. So, M plus X and M plus 2X, they are both in cap M. Hence, X is equal to M plus 2X minus M plus X, but this is in M minus M. So, W is contained in M minus M. Here we use that W is closed under scalar multiplication. Next, now assume that W is in M minus M. Well, then we need to show that W is in W, cap W. Well, then W is equal to X minus Y for some XY in M. Now, however, since cap M is this M plus W, X is equal to m plus x prime, and y is equal to m plus y prime for some x prime in W and y prime in W as well. Hence, W is equal to, that's x minus y, that is m plus x prime minus m plus y prime, but that's equal to x prime minus y prime, where both of these belong to W, but this difference then belongs to W, since W is a subspace again. Hence, we also have that m minus n is contained in W, so W is equal to m minus n. This in particular yields the following corollary. If M is an affine subspace of Rn, then M minus n is a subspace of Rn. The proof is already here, but this observation now allows us to assign a dimension to any affine subspace. Well, we will simply assign the dimension of the subspace M minus n as the dimension of the affine subspace M. That M be an affine subspace of Rn, the dimension dim of M is defined as the dimension of M minus n. We know what the dimension of a subspace is. Well, let me write this once more. Let M be an affine subspace of Rn. Now, M is equal to singleton M plus M minus n. Now, this part we already know, but this will be the case for any M in M. So I can take here any M in cap M, so this sum will stay the same. The proof is simple. It's left as an exercise. Now, when we talk of points, lines, planes, then let's go back to analytic geometry and try to remember what's going on there. Now, if you have 2 points, x, y, in R2, say, there is a unique line passing through them if x and y are different, x, y are different. if they're the same, there is again a line passing through two of them, but there are an infinite variety of such. Well, so each point on this line should be representable just in terms of x and y. From analytic geometry, you know, if you write this combination for any r in R, well, when R is in 0, 1, you will get this part. In fact, when R is 1, you will get just this point. When R is 0, you will get just y. When R is less than 0, you get this portion. And when R is larger than 0, you get this portion. In fact, Rx plus 1 minus Ry, no matter what real number R you take, will lie on the line passing through x and y, and any point on that line has a representation of this form for some R. But this is not peculiar to lines. This is peculiar to all affine subspaces. Now, our first theorem here is let M be a non-empty subset of Rn. Now, M is an affine subspace of Rn if and only if for all xy in M and for all R in R, we have Rx plus 1 minus Ry in M. Now let's start with the only if part. Assume that M is an affine subspace. Assume that M is an affine subspace of Rn. Now, all we know so far is the definition of an affine subspace. M is equal to singleton M plus W for some M in M and some, well, in fact, we know this is M minus M, so let me write it just by this. Now this is equal to M minus M. In fact, for any M in M. Well, we need to show this, so let us take any xy in M and R in R. Let xy be in M and R in R. Now let's look here. We wish to show that this holds. Yeah? But now when x and y are in M, here, look, this is Rx minus Ry plus y. So it's R times x minus y plus y. But x minus y, if x and y are in M, they will be in here. But this is a subspace, so R times x minus y will be in there. But now y is in M, so I can take this as y. Now, Rx plus 1 minus Ry, this is equal to y plus r times x minus y. Now x minus y, this is in m minus m, but this will be in m minus m as well, since m minus m is a subspace. Of Rn. But then this is in singleton y plus m minus n. But this proposition tells, well, for any m in cap m, thus also in particular for y, this is equal to m. Hence, if m is an affine subspace of Rn, then this holds. Next, the converse. Conversely, assume that for all xy in M and for all R in R, we have Rx plus 1 minus Ry is again in M. We should show that then M is an affine subspace. Now here, it is given that M is non-empty. So let us pick some M from cap M. Since M is non-empty by hypothesis, pick some M in M. We will prove that M is an affine subspace in 2 steps. First, we will show that the set cap M is equal to the singleton M plus cap M minus cap M. But that will not suffice because we know cap M minus cap M is a subspace if cap M is an affine subspace. But then we will separately, in the second part, show that cap M minus cap M is a subspace of Rn explicitly. Claim M as a set is equal to this M we have taken plus this. So take any x in M. That should belong to this set. But that's easy. Now, x is equal to M plus x minus M. But x is in M is in M, so this is in singleton M plus M minus M. So M as a set is contained in singleton M plus M minus M. Next, the converse. Take any, say W, for example, in M plus m minus m. We should show that this belongs to cap m, W. But if W is in here, then W will be equal to m plus x minus y for some xy in cap m. So we need to show that this is in cap m. Now, it's like a Sunday's puzzle, and we have to use this. Now, by hypothesis, two m plus 1 minus 2y, this is in m. Because m is in cap m, y is in cap m. This is, if r is 2, then this will be this. Likewise, 2x plus 1 minus 2y, that's in m. That is 2m minus y and 2x minus y, they are both in m. But I can now apply this hypothesis to these two members of cap m by choosing r appropriately. How would you choose r? If you choose r 1/2, 1/2 this plus 1/2 this, you will just get m plus x minus y. By the same hypothesis, one half 2m minus y plus 1 minus r is 1/2 again, 2x minus y. This belongs to m. But so this is m, this is plus x, and here we have minus 1/2 y minus 1/2 y minus this, but this is nothing but w. So we have shown if w is any member in here, it belongs to cap m. So m plus m minus m, that is contained in m, hence m is equal to singleton m plus cap m minus cap m. Now the next step is to show that m minus m is a subspace of Rn. Now, well, is m minus m non-empty? Yes, since m is non-empty, m minus m is non-empty. In fact, take any x in m, x minus x, 0 is in m minus m. Well, then we'll show that first that it's closed under scalar multiplication, and then it's also closed under vector addition. Conclude that it's a subspace of Rn, and that'll complete the proof. But let's continue with the rest of the proof next time.